radar problem. I'm not sure whether you are familiar with radar, but basically it's like you send some information to the environment, and if there's a target, the transmitted signal will be bounced off, and part of the reflected signals will be received by the receiver, right? So TX means transmitter, RX means receiver. So this is what a radar does. So what is MIMO radar? MIMO means multiple input, multiple output. So that means you have a bunch of transmitters. Say you have 1, 2, in total, capital M transmitters. So towards this channel, it's like you have multiple input to the channel, right? So what is multiple output? That means you have a bunch of receivers, right? So you receive signals from reflected signals contributed by lots of transmitters. So you have multiple in and multiple out. So that's why we call it MIMO. And what do I mean by cloud MIMO? So it's a new idea. So, but the idea behind it, I mean, the theory behind it is not that new. It's kind of what do we mean is because of the, coming 5G or 6G, we are going to talk about like Internet of Things. So the radar can be used in many, industrial applications. So you might have a lot of receivers, a lot of sensors. So they're going to collaborate they receive signals and they send the signals to a fusion center, possibly via a wireless way, right? So if they do this, you need to think about the communication burden between the local receivers and the fusion center might be huge. So this is a problem we need to think about. So to solve the issue, we're thinking of, instead of transmitting the raw data, I think no one will do that because we're likely to use a wireless channel. So that's why usually we have to think about quantize the data you received at each of the local sensor before you send them to the fusion center, right? So for this cloud memory, the quantization is very important, right? So we're going to talk about how you should pick your quantizer, how could you design your parameters in order to ensure the overall performance, but at a affordable cost. So for example, the bit rate for each of the local sensor is limited. So this is one of the most important constraints we're going to consider in our later analysis. Okay, so let's assume the locations, because we're thinking about this is an active radar, right? So if you have a passive radar case, you can do similar analysis. Just suppose this is an active case, so you know the signals transmitted from its transmitters, and you know the locations of each of this transmitter. Say we denote by X, T means transmitter, and YT means location along the y-axis, since we are considering a two-dimensional case for simplicity. So suppose you know all the location of the transmitter and all the locations of the receivers, and you know all the locations and you know all the transmitted signals. So what you are going to do is you want to make use of the observations and all these sensors and think about how to process the signals in order to make a better detection or estimation. So the signal model looked like this. Say we have a bunch of transmitter to receiver paths. So it's like each of the signals transmitted by each transmitter can be received by each of the receivers. So without loss of generality, let's think about only one transmitter to receiver path. So we consider the signal transmitted by the EMS transmitter and bounced off the target. If there is a target, assume there is a target, then the signal will be bounced off and being received by the EMS receiver. We only consider this NM's path, right? So we use this, and you can do similar analysis to any of the transmitter to receiver paths. So the received signal at the N's receiver contributed by the M's transmitter at time instant K. Suppose you want to sample the received data. So you have a discrete time version. So the signal look like this. So in this signal model, you have this capital E, meaning the transmit energy. Suppose that energy transmit for each of the transmitter, they are identical. So that's why you have E over M. So this is like the total transmit energy. M is the number of transmitters. So this Sm of SKTS. So K is a time instant, TS is a sampling period, right? So this is a sampled version of a signal, and it's getting delayed because of the target reflection, because of the channel. So you get delayed version. So Sm means the signal transmitted at the M's sensor. Okay, so this is a reflection coefficient. It counts for all the propagation loss or target reflection or anything you can think about, right? So they are all counted into this zeta m times m. And this F is a Doppler shift. So possibly the target is moving, and you get a Doppler shift associated with different transmitter to receiver paths. And this tau mn is the delay due to the propagation from the transmitter to the target and then to the receiver. So different paths may have different time delay and different Doppler shift. And this W, it's an additive noise. It could contain some clutter or some other interference, but suppose we have done some pre-processing. So right now you only have some residue or some, let's assume it's Gaussian noise, right? So it is supposed to be white in both space and time. So that's why we denote the distribution of it by complex Gaussian with the correlation like this. So the expected value of the WMN K and WNN conjugate K prime, meaning they are white in time. And also we assume it's white in space. So that's why we don't have N prime here. So you must have the same transmitter to receiver path and the same time. Otherwise you have zero noise variance. Okay, so this is all about our model. And later on, what we're going to do is, because we want to analyze the performance, right? You want to analyze the performance, that's why you have to look into this model. But next, what we're going to do is, suppose this is what you observed. So what you're going to do is, you want to quantize this guy. You want to do the quantization because the further processing will be done at the fusion center. So you want to quantize this. But our assumption about this received signal is complex. So you can do like IQ processing at the receiver. That's why you usually can denote the received signal by a complex version. But if you are going to quantize it, you have to take the real part and take the imaginary part. You have to divide the complex data into two parts before you do the quantization. So we denote the whole stuff, the useful signal part, like this is the signal bounced off from the target, right? The signal part, we denote it by mu mn of k, right? So the overall signal, as we said, you want to take the real part of the overall received signal and also take the imaginary part of the overall signal, and then you quantize them. So a usual way to quantize this complex data, I mean, it's real and imaginary part, is you use the same quantizer, but you use two quantizers with the same design. So you quantize them simultaneously and you add them up. So that is a quantization of the complex data. So after you are done with the quantization, you can send it to the Fusion Center. So let's deload the quantization output by QMN of K, right? So you do this at each of the local sensor for each of the transmitter to receiver paths. Suppose all the transmit signals are separable. Okay, suppose the quantizer, so let's look at the quantizer. So the quantizer is kind of doing a mapping from the input to the output, right? So the quantizer input, we can deload it by gamma, and you're looking at which region this input falls into. So in total, suppose your quantizer has B bits, right? So the number of bits of the quantizer, let's deload it by B. So in total, how many regions you have? You have 2 to the b's power, right? Suppose you have a B-bit quantizer, so the quantized output can take on one of the de-quantized values. Okay, so this B, the number of bits of the quantizer, it has to do with the bit rate, right? Because if you have a B-bit quantizer, the message you send out has this number of bits. So remember previously we said, due to the communication burden, a very important constraint we consider in our work is bit rate. So this is a definition of bit rate. Bit rate is the product of the number of bits times the sampling rate, right? So in our work, we suppose this bit rate is fixed. So you can see, because it's a product of these two things, if you want to increase the number of bit with a fixed bit rate, you have to reduce sampling rate. So later on, we're going to think about whether you should have a bigger number of bits or should you have a bigger sampling rate. So which benefits you more in terms of performance. Okay, so just now we said this QMN of K means output for the MN's transmission path and the K's time instant. Suppose in total, we have capital K time samples, and of course you have to take into account all the transmitter to receive paths. You have a total number of N times N transmission paths. So you just collect all of them, right, in certain order. You don't have to worry about the order, but just think about you collect all of them, all the spatial and time samples, and they all together will give you the quantized vector. Okay, so this is what you send out. You will send out from the local sensor to the Fusion Center. So here is what you send out, the capital Q. So all the quantized data will eventually be observed by the Fusion Center. Just let us think about, the phase synchronization, the time synchronization, everything has been done. Let's don't worry about it for now. And let's think about the channel for the transmission between the local sensor to the Fusion Center is ideal, because we are going to think about the signal processing and what is the best approach. So let's just assume for simplicity only, the channel is ideal. If it's unideal, you can add some other interference to this. But for now, let's assume what you observed is exactly equal to what you sent. Even for the simple case, we have a lot of things to do. That's why let's just keep it simpler. Okay, so what you received at the Fusion Center is exactly equal to what you quantized. So now at the Fusion Center, what we're going to do, like the topic of today is you want to do first of all target detection, right? You want to tell whether there is a target or not. So this is a so-called detection problem. So we have to solve, I mean, you don't have to, but let's solve it using a Bayesian approach, right? So you formulate a hypothesis testing problem. So under H0, that means there's no target, right? So no target. So what you are quantizing is, it should be like the received signal used for part and plus noise. But if there's no target, what you're quantizing is essentially the noise only, right? So under H0, there's no target. What you really received is equal to what you quantized, is exactly equal to the quantized version of the noise. So under H1, alternatively, that means there is a target, right? So what you received is a quantized target reflection part plus noise, right? It's real part, it's imaginary part. So anyway, this is just a detection problem, hypothesis testing problem. No target, hypothesis H0, target exists, hypothesis H1. So you want to tell between H0 and H1, right? Decide for either of them. So in order to formulate the optimal detector, we take the likelihood ratio test, take the likelihood ratio approach. So if you have learned signal detection estimation, I think you should be familiar with this. So all you need to do is to compute the likelihood function. So likelihood function in formulation is equal to, I mean, at least the expression is equal to the PDF of this quantized data. So all you need to do is to figure out what is a probability density function of this quantized data. And you think about the joint distribution of them. So you can have that expression, which is equal to the likelihood function. Right. So you take them computation, and eventually you're end up with a likelihood function under H0 and under H1. So that means if there's no target, what does your observation look like? And what's the distribution of it? And it has to do with its likelihood function. And you compute all of them. And we're not going into million details, but just think about you have to treat all this stuff. And this is the output of the quantizer. And it is a random variable, and it is a discrete random variable. Okay. So that's why in order to compute its PDF, it's a little bit complicated. You have to think about what is the distribution of it, and think about, you know, the Q function because it's supposed to be Gaussian and things like that. So eventually you will end up with something like this. So this is a probability mass function actually because it's discrete. So given this likelihood functions, you can be able to, this is just part of it, right? You need to compute all of them and take the product of them, and then you have the result of this vector, observation vector. So if you take the ratio of these two guys and do some manipulation, and you end up with a likelihood ratio. So the likelihood ratio, you can use it to compare it to threshold. If it's above the threshold, you're designed for H1. If it's below the threshold, you're designed for there's no target. So this is nothing but the ratio of them, right? So PYH1 over PYH0, that is a A of Y, right? It's a function of your observations. It turns out, all I want to say is, it turns out the detector look like this. So you have the observation as input and the decision as the output, right? You decide for target exist or target absent. And just look at this computation. It looks a little bit complicated. And if you want to go further to determine its performance, you are going to further consider what is the PDF, what is the distribution of this guy. So it seems impossible if you want to go further to compute, well, how likely this guy is going to be bigger than the threshold. So you are going to take into account the distribution of this guy, and you see this is a Q function, and your input data is somehow inside of it. It's very difficult. So you don't have an enclosed form for the detection probability. So that's why we're going to try to find some other ways in order to get some analytical result. Of course, if you want to do numeric evaluation, you can go ahead. It's doable. But if you want to do analytical analysis, it's very difficult. So if you are going to design a system using this result, it's also very difficult, right? So you can tell, the detection performance is somehow determined by all the system parameters which are embedded in these parameters, but you cannot tell how, and you cannot tell the trend. So that's why we're very interested in getting some analytical result. So our approach is to do the approximation. So instead of quantizing, instead of doing the computation directly, as we did before, we think about another way. So this is a direct computation, right? So this is a quantization output is equal to the quantized real part plus the quantized imaginary part. Alternatively, now we do another stuff. Let's assume the quantized output is equal to the quantized input plus a noise. And this noise is a so-called quantization error, or you can call it quantization noise. And this guy accounts for all the stuff the quantization did to the input, right? So output is equal to input plus a noise. And we did some, survey and did some research. It turns out, this is a practical assumption, actually. If you have a b-bit uniform quantizer, uniform means the quantization step is identical, right? So if you have a b-bit uniform quantizer, so it says as long, actually we did show that by ourselves, as long as your quantization step is small enough compared to the noise of the input signal, right? Because your input signal is what you received at the local sensor. It is also a noisy version. So as long as your quantization step is small enough, so it turns out the distribution of the quantization error can be predicted. So it's nothing but the quantization step squared over 12. So we can carry on the further analysis, and we can skip the details. It turns out in this case, you can very easily write down the distribution of the quantization output because it's Gaussian, right? Gaussian plus Gaussian gives you another Gaussian. You know how the PDF of Gaussian look like, so you can have the likelihood ratio in a very simple form, right? So you have the likelihood function for the H0 and H1 hypothesis. You can again take the ratio and do the Neiman-Pearson or any other detection you like. And it turns out the computation is rather easy, right? So it turns out you have this test statistic and you can now consider the distribution of this guy. And then you can have a closed form solution for the detection probability. And this is what we obtained. I think maybe you're not interested in the detail, but this is what we obtained. It's a Q function and a bunch of known stuff. It turns out if you plug into the stuff we defined earlier, this is what you end up with. Q is a Markov Q function, right? So this is a inverse function, and P far is supposed we use Neiman-Pearson detection. So the probability of false alarm is predetermined. So this is a given value. So you just look at this guy, you can see the detection probability has to do with all the parameters inside of this, under this square root. So two important things we want to emphasize is, this has to do with the noise, has to do with the radar parameters, but it also has to do with, you see this B, the number of bits, and this Fs, the sampling frequency. So these two things what we want to analyze, we want to emphasize, but of course you can use our result to analyze, to optimize any other system parameters. But now let's focus on this number of bits at sapling rate. Okay, so suppose we fix the bit rate. So the bit rate is the product of B and Fs, right? Suppose R is fixed. So you can say B is equal to R over S, right? So you plug this B equals R over S, you can say eventually it's a function of any of this, any two of these three things. So why we do this, we want to say, suppose you have a fixed bit rate. What you can do is you can try to figure out what is the best FS that can optimize, that can maximize this detection probability, right? So you can take the derivative of this guy with respect to FS and you let it be 0, then you can find the FS which maximizes detection probability. Okay, so let's look at some numerical examples. Suppose you have a MIMO radio system which has 2 transmitters and 3 receivers. You have a transmit signal which is a single Gaussian pulse, and this is an observation interval, and this is a frequency distance between different transmitters because you want to use it to make sure the signals are orthogonal with each other, and you have a possible target if target exists. So that means this is a cell under test you're looking at, right? So the potential velocity look like this. So the noise has this variance value, and the signal to noise is defined like this. That's overall received signal power over the noise power. And suppose this is a dynamic range of the quantizer, we just use this without loss of generality. You can switch the value as you like. And suppose you have a false norm level like 10 to the minus 3. This is actually slightly big. Usually in practice, you want to make it even smaller, but you know, we don't want to increase our computational burden. That's why we just leave it as is. So you see, this is what we observed. So we're plotting the probability of detection, correct detection. You want to make it as big as possible, right? And then this is plotting versus the signal to noise ratio, right? So you can see for each curve, as long as you increase the signal to noise ratio, the detection probability increases as expected. And we have a bunch of curves. Say you have, for each color, different color means different number of bits, right? This means the number of bits is equal to the blue curves, number of bits is equal to 2. And this dashed curve means you are doing the direct analysis. You didn't do any approximation. You did just do exactly what you did, right? You used a discrete random variable. You compute everything needed. So this is what you obtained. And the solid curve is an associate one, but you use the Gaussian approximation. Gaussian approximation use a Gaussian quantization error. And you can see when the B number of bits is small, when it's equal to 2, the distance between them is slightly big, right? If you have a 1-bit quantization, the distance is even bigger. But you see, fortunately, say this red curves, again, dashed line and means the approximation, and the solid line means the direct analysis. You can see the distance between them becomes much smaller. This is B equals 2. This is B equals 3. You only increase 1 bit, and you can see the difference becomes very small. This is reasonable, and this agrees with our analysis, right? Because you are giving a fixed dynamic range. So if you increase the number of bits, your quantization step becomes smaller, and the condition we set will be satisfied. So that is why this is telling you, as long as the number of bit is bigger than or equal to 3, you can use our Gaussian error approximation. So you can have a very simple way to analyze the quantization output. So if we keep on increasing the number of bits, you see you have 4 bits for the black curve, and this purple curve, you have 5 bits. You see they are almost, the curve are on top of each other. So that means there's no loss for approximation. You can use it. And there's another curve. You see, this is a blue curve. That means a case for unquantization. So suppose you don't quantize things. Suppose you have very powerful communication channel and you just send what exactly you observed. So this is ideal case. That's not going to be happening in practice, but we plot it as a benchmark. So it turns out, you see, as long you have, this is the purple curve means you have 5 bits quantizer. You can see when you quantization bits is 5, it's not that big. Your performance, your overall performance is very, very close. I think it's close enough to the unquantized case. That means in this case, your quantization does not hurt you much, right? So, and you can use our approximation to do the performance analysis. So it will work in practice. But of course, you have to take into some undue background, like the channel between the local sensor and the fusion sensor. You have to think about like the clutter interference, something like that. But I think this is a very important first step. Okay, so for the second example, what we did is we fixed the number of bits. We fixed the number of bits, but what we did is we changed the number of sapling. We changed the value of sapling rate, right? The sapling rate. You see, this is the sapling rate when Fs is equal to 200 hertz. And then this is 300, this is 700, 1200, 1700, and 2200. You can see as you increase the sapling rate, your performance gets bigger and bigger, right? Gets better and better. So from these two examples, you know, you can increase the performance either by increase the number of bits or by increase the sapling rate, right? But there is another trend, another interesting observation is, you see, if I go from 20 to 700, the increase is huge, right? This is increase of PD for a given SNR. But if you further increase the number of the value of sapling rate, the incremental gets smaller and smaller. The same thing for the number of bits, right? You go from 2 to 3, you get a huge increase. But if you further go from 4 to 5, the increase gets smaller. So we will need to think about, well, what's the best approach, right? Of course, you want to have infinite memory rate, but that will cost you a lot. So you want to find a reasonable value for them. And the most important thing is the product of Fs and the product of B is fixed for the case of constrained bit rate. So you still have to trade off the bits and the sapling rate, right? Because we know you want to increase bits and also increase sapling rate. The increase of both will increase the performance, but there is a trade-off between them. So what we did here is we fixed the constraint. We fix the bit rate, right? The bit rate. So we fix the product of B and Fs, and we plot the detection probability versus the sapling rate. So it turns out if you, for each of the given, so we have 4 different figures. For each figure, we have a fixed bit rate. So you see, if you increase the bit rate from like 900 to like 3,600, you can see overall the PD increases. If you look closely at these values, you can see this 0.2, 0.8, this is 1, this is 1, and this is 0.6, this is 0.88. So generally, as long as you increase the bit rate, the performance will be increased. But for each of this figure, it's plotted for fixed bit rate. You can see as long as you increase the number of rate, the performance increases in the beginning, but later on, it drops off. So that means if you continue to increase the sapling rate, it's not going to always increase the performance. Why? Because you have a fixed bit rate. right? So when fs is bigger, that means your number of bit is decreased. So it will hurt you. So there is always a trade-off between the fs and b. So when you want to stop increasing fs, you just stop in the peak value. So you should stop here and stop here, stop here. So this guy, this example tells you, you can find the optimal sampling rate by looking at the performance. Okay, so that's all about detection. And later on, I will go very quickly about the estimation because all the signal model are very, very similar. Right? We use similar signal model. This is a repeated step of the previous slide. But now the problem is, so previously we're looking at detection problem. That means we're looking at the given cell under test, and for a given Doppler shift, maybe you have a shifted version of Doppler. That's why everything is known, and you want to tell whether this guy exists or not. But now we're doing the estimation. That means suppose you know there is a target, there is indeed a target, and you want to make sure you understand what is a detailed, what is a fine position, right, of the target. Oh, thank you. Okay, so you want to tell the location of the target, and the location of the target has to do with the delay. And also, the velocity of the target is also the parameter of interest to us, and it has to do with Doppler shift. So in other words, this is a parameter we're interested in, the target location and the target velocity. Okay, so you have the same signal model and you want to do another problem. You want to figure out what is the location of the target, what is the velocity of the target. And we're going to do the quantization, do the fusion in order to figure out the values of the location velocity. This is what we're going to do later. Okay. Oh, how can I? It seems. Okay, so you do similar stuff. Don't know how to erase it. Okay, forget it. So what you do is you again do the quantizer and you send the quantized received data to the fusion center, and now the fusion center will estimate the parameter of the parameter of interest. And what you do is you formulate some estimation problem, and we use a maximum likelihood estimator. Again, you compute at the fusion center, you compute the likelihood function, you take the log and you find the parameter which can maximize this guy, and this is what you have for the ML estimate, right? So the key point is, again, try to calculate the likelihood function. And as we showed you before, it's very similar for the estimation problem. You can do either direct analysis and you have to deal with a direct random variable, or you can do the Gaussian approximation. So I'm going to skip the following slides. So what we're doing is we compute the PDF of this guy or compute the likelihood of this guy, right? And then to analyze the performance of estimation, a very popular metric is a Kramer bound. Kramer bound tells you what's the best mean square error performance. So if you go to the textbook, it tells you the Kramer bound is nothing but the inverse of the Fisher information matrix. Don't worry about the Fisher information matrix. It's just some calculation. You can go from the likelihood function to the Fisher information. Just plug into formulations in your textbook and you'll figure out the result, right? And because, the received signal is a direct function of the delays and Doppler shifts as we looked at before, but it's indirectly a function of the locations and velocities. That's why we use the chain rule to compute the film, right? So anyway, this is the details. We don't want to go through it. Just look at it. It looks very, complicated, very lengthy because we did a direct analysis. This is a very messy function, but you can write it down. We did do the derivation. But the alternative way is, again, you use the Gaussian quantization approximation, but right now you're doing the estimation problem. You do the same thing, and it turns out the future information and also the Kramer bound look very friendly. And again, your calculation can be made in closed form and looks very nice and beautiful, and you can do some further analysis, optimizations, whatever you like. And this is a numerical result. And we said, we did we did both cases. We did for the direct analysis, we compute the Kramer bound, and we compute, this is a simulation result. We compute the mean square error. It turns out to be, on top of the Kramer bound for the big enough SR. It tells you our calculation, our derivation is correct for the direct analysis case, because you see these blue curves are for the Kramer bound. This is for the location along the x-analysis, on the y-analysis, and velocity on the x and y-axis, axis. So the same thing we do for the Gaussian quantization approximation case. All these figures just trying to show you our derivation for the Kramer bound is correct, right? So because the calculation of Kramer bound is rather simple compared to the calculation of mean square error, it's going to be very time consuming. So if you are going to do some real-time analysis, usually you want to use a Kramer bound rather than the mean square. So the previous slides, like this one and this one, we want to show you the derivation is correct. That's why later on we can only use a Kramer and forget the mean square error, because the computation of this mean square error is very hard. So now we only keep the Kramer bound. So what we're doing is we do the comparison. Again, we increase the number of bits. It turns out the bigger number of bits will help you, right? And also the dashed line and solid line means approximation and the exact direct analysis. It tells you, when your number of bit is big enough, say the number of bit is bigger than 4, the approximation is good enough. And also if you have, big enough number of bits, say when the number of bits is bigger than 5, you can have an estimation result, which is almost equal to the unquantized case. And, actually we're done with the estimation, but a little bit more is just now we are quantizing what you observed. You're quantizing the received data. The alternative way is instead of quantizing the received data, we can hold on for a second. We don't do quantization, but we do the estimation for the time delays. So that means at each sensor, local sensor, you first of all do the estimation, and then you quantize the time delay. So the time delay, it's only a scatter. It's a scatter. It's much easier than quantize the received data. And you do similar stuff, And it turns out, okay, see here. So it turns out if you quantize a time delay, you have a estimation performance look like this, which is in red. And the black curve is what you do for quantizing the received data. And you can see there's a cross. That means for small k, k is a parameter of the system. For small k, you can see it's better for you to quantize received data. But for bigger k, it's better for you to quantize the time delay. So it's up to you, up to your system, up to your application. Okay. So here is a conclusion. So what we introduced today is we talk about detection and estimation for the cloud MIMO radar. And very importantly, we did quantization. And we did both direct analysis and Gaussian approximation, and we showed like the approximation works in most of the cases of interest. And yeah, we look at the trade-off between the number of bits and sampling rate. And we also talk about, actually we did some analytical derivations, but we don't have time to show you. So you can quantize the received data or the time delay, and you can cleverly adjusting your system parameters to use either the received data quantization or time delay quantization. So it's up to you. And I think all our analysis can be useful to guide the system designers. And for the details of our work, you can go to our papers. And this work is, a collaboration with my student, Jin Wang, and my collaborator, Professor Rick Blum in Lehigh University. But I think that's all, maybe. It's taking too long. Sorry about that. I think that's all for my presentation.
Thank you very much, ma'am, for sparing your time for today's webinar. It was indeed a very informative session. I request the participants to drop their queries in the chat box.
ज़्यादा दिमाग मत लगा अपना, हाँ ठीक है.
Should I
I
stop
request the
sharing?
participants to... Yes, ma'am. I request the participants to drop their queries in the chat box. Now, I would like to request Dr. Archana NV, Treasurer, IEEE MYSO Subsection, Professor and Head, Department of IEEE, NIEIT Mysore, to give the concluding remarks about the session.
Good evening. Good evening, one and all. It was indeed pleasure to listen to Professor Q.N. Hay. Ma'am, your presentation was technically too good. We learned about the cloud MIMO radar, which is a novel technique, and reduction of communication burden. Detailed mathematical modeling actually helps the researchers who are doing their research in the above areas. Ma'am, your explanation about signal model, target detection, parameter estimation was truly excellent. The numerical study parameters actually helped us to understand the concepts better. Thank you, ma'am. Looking forward to listen more from you. Thank you, ma'am.
Thank you.
Thank you, ma'am, for your valuable remarks. As we've come to the end of the webinar, I'd like to convey my deep regards and hearty thanks to the resource person of today's webinar, Dr. Q.N. Hay, ma'am, for accepting our invitation. Thank you, ma'am.
Thank you very much.
On behalf of IEEE MYSO subsection, I request you to accept this virtual memento as a token of gratitude. I'm extremely grateful to Dr. Bindu A. Thomas, Chair, IEEE MYSO subsection, and Dr. Parmesha Chari BD, Chair-elect, IEEE MYSO subsection, for the support and guidance for organizing this webinar. Thank you, ma'am. Thank you, sir.
Thank you.
Thank you so much.
Thank Dr. Archana NV, Treasurer of IEEE MYSO subsection, for her support in organizing this event. Thank you, ma'am. My sincere thanks to all EXCOM members for their support in organizing this webinar. My special thanks to all the faculty and student coordinators for their timely support and teamwork in conducting this event successfully. I wholeheartedly thank all the participants for making time and attending this webinar. I hope this session was fruitful to you all. Once again, I thank each and everyone present here for making this event a grand success. I would like to request all the participants to acknowledge the upcoming webinar series till 29th of March 2021 and extract knowledge from it as much as possible. I once again thank you all and have a pleasant evening. This is Prathana MR, your Master of Ceremony, signing off. Thank you.
Professor Kuyan, thank you. Thank you very much for the wonderful speech.
Thank you. Hope we can
Thank
see
you.
you again.
Yeah. Thank you. Bye.
Bye.
Bye. Thank you to participants.
Thank you, Prathana. Thank you, Skanda.
Thank you, ma'am.
You're welcome. Thank you.
Skanda, thank you.
Thank you, sir. Thank you.
Thank you. Bye.
Yes, sir.
Thank you.
Thank you, sir. Bye, sir.
Bye.
Bye, sir. Birthday.
Thank you. Thank you. Bye.
Yes, sir.
Okay.
Thank you, sir.
Thank you, madam.
Thank you, sir.